Hey everyone, my name is Joe, and this is Something with Joe. This is the first video in a series in which various scientific topics will be discussed. And this week's topic is from chemistry, and it's the mole. In this video, we're going to be running through what the mole is, how it's used in chemistry, how it relates to mass, and the involvement of a particular number known as Avogadro's number. Now the reason why I've chosen this topic for the first video is because when I and some friends in college were first introduced to the mole, it caused us a bit of a headache. There are a few tricky little details in this topic, but once I figured out the mole, learning everything else in chemistry and the other sciences just seemed more possible. So let's get to it. So what is the mole? The mole is an SI unit that expresses a measurement of the amount of a substance, which could consist of atoms, ions, or molecules. The first thing to note is that when we say amount, we mean something different to mass. Mass refers to how heavy a sample of a substance is, whereas the amount of a substance refers to the number of particles of that substance present in a sample. Let's consider an example. Let's say we have 50 grams of magnesium chloride. The mass of that sample magnesium chloride would be 50 grams. However, if we wanted to know the amount of magnesium chloride present in that sample, we would have to consider the number of ions of magnesium and chloride present in that sample. Or, for another example, let's say we had a piece of cake, and in that cake there was 40 grams of sucrose, table sugar. Now 40 grams refers to the mass of sucrose present in that piece of cake. However, if we wanted to consider the amount of sucrose present in that piece of cake, we would have to consider the number of molecules of sucrose present in that cake. So, to quickly recap, mass refers to how heavy a sample of a substance is, whereas amount refers to the number of particles of that substance present in a sample. Okay, let's now delve into the part of the topic that caused me and my college peers a bit of a headache when we first encountered it. I'm referring to Avogadro's number. This is Avogadro's number, 6.02 times 10 to the 23rd. This number is crucial in the world of the mole, because it signifies the number of particles that are present in 1 mole of a substance. Let's briefly explore that number. It is written in standard form, also known as scientific notation, which is a way of expressing either a really small number or a really large number, and in this case it's a very large number. I won't go into too much detail about standard form or scientific notation in this video, but if you want me to make a video on scientific notation and standard form only, then please leave a comment down below. The number, if written out in decimal form, would look like this. This is 602 hexillion, which is a very large number. And if we were to write out this number every time we wanted to record the fact that we had 1 mole of a substance, it would take up a lot of time and paper. So we tend to write things out in standard form in order to make things a little bit easier. But why is it called Avogadro's number? Well, it was named in tribute to an Italian physicist named Amedeo Carlo Avogadro. Avogadro was known for his work on the behaviour of molecules of gases at different temperatures and pressures. He went on to devise Avogadro's law. We'll discuss Avogadro's law in another video. But why is Avogadro's number part of a principle known as Avogadro's constant? Well, it's because 1 mole of a substance, no matter what that substance is, contains the same number of particles as there are atoms in 12 grams of carbon-12, namely 6.02 times 10 to the 23rd. We'll get to carbon-12 in a bit. So let's say we have 1 mole of carbon dioxide molecules. In that sample we will have 6.02 times 10 to the 23rd carbon dioxide molecules. Alternatively, for the sake of dietary balance, because we had a piece of cake earlier on, let's say we had 1 mole of apples. In that sample we would have 6.02 times 10 to the 23rd apples. The point is that whenever you have 1 mole of anything, no matter what the substance is, within that sample you will have 6.02 times 10 to the 23rd entities of that substance. Hence the phrase Avogadro's constant. So why do we measure in moles? The main reason why we use the mole is because it is an internationally recognised way of calculating and measuring the amount of a substance. Remember when I referred to the mole as an SI unit earlier on? All this means is that it is an internationally recognised way of measuring a certain quantity, and in this case, it's the amount of a substance. Okay, let's now address how mass influences the calculation of the amount of a substance in moles. I'm going to use a definition of a mole that you will see in textbooks. 1 mole of a substance contains the same number of particles as there are atoms present in 12 grams of carbon-12. What this statement refers to is that if you were to calculate the number of moles of carbon-12 atoms present in a 12 gram sample of carbon-12, the answer would be 1 mole. Let's see how that comes about. Okay, To understand how mass influences how we calculate the amount of a substance in moles, we need to understand 4 different variables. Now the term mass is included in the names of all 4 of these different variables. However, the meaning of the term mass varies depending on which variable you are talking about. These 4 variables are relative atomic mass, relative isotopic mass, relative formula mass, and molar mass. Let's consider relative atomic mass and relative isotopic mass first. Relative atomic mass is defined as the average mass of one atom of an element, considering all of its isotopes and abundances, compared to 1/12 of the mass of one atom of carbon-12. Whereas relative isotopic mass is defined as the mass of one atom of an isotope of an element compared to 1/12 of the mass of one atom of carbon-12. The term isotope refers to an atom of an element that has a different number of neutrons in its nucleus in comparison to atoms of the same element. However, it has the same number of protons and electrons as atoms of the same element, as indicated by its atomic number. Now the reason why I'm talking about relative isotopic mass and relative atomic mass together is because relative isotopic mass plays a crucial role in the calculation of relative atomic mass. In order for the relative atomic mass of an atom of an element to be calculated, we must consider the relative isotopic mass of each isotope of that particular element, along with each isotope's abundance. I won't go through the process of calculating relative atomic mass in this video, but I will make a separate video showing how relative isotopic mass plays a crucial role in the calculation of relative atomic mass. However, I will say that the value of the relative atomic mass for an atom of each element is usually expressed in either 3 significant figures or 4 significant figures, and is expressed for each element in the periodic table. Now the reason why we talk about the mass of 1/12 of the mass of one atom of carbon-12 when discussing relative isotopic mass and relative atomic mass is because the mass of 1/12 of the mass of one atom of carbon-12 is one atomic mass unit. An atomic mass unit is the unit of measurement we use to express the mass of an atom, rather than grams. I know, it's another little tricky detail, but there is a good reason for this. The mass of atoms are pretty difficult to figure out, and the most accurate way we can deduce the actual mass of an atom is by comparing atoms of all elements to a particular atom, which is carbon-12. Carbon-12 is the most abundant isotope of carbon, and the reason why we talk about it so much is because it sort of acts like a benchmark when we consider the mass of all other atoms. Okay, let's now move on to those other 2 variables. Relative formula mass is the sum, or total, of the relative atomic masses of atoms present in a compound, and this variable doesn't have any units. Now our 4th variable is molar mass. This describes the mass of 1 mole of a substance, and is expressed using the units of grams per mole. However, despite the fact that relative formula mass and molar mass could be the same numerically, they do differ in meaning, and you could be asked to define either one or possibly both of these variables in an exam. Okay, let's now move on to some calculations, and let's prove that 1 mole of carbon-12 atoms are present in 12 grams of carbon-12. To calculate the amount of a substance in moles, we need a formula. I know, there's 2 formulas on the screen, but there is a good reason for this. Some exams will allow you to calculate the amount of a substance in moles using relative formula mass as a variable. However, in other exams you may be asked to define molar mass and use that as a variable in your calculation. In this video I'm going to be using both formulas for our calculations, just to show how both variables can be used. Let's start with a formula that involves using relative formula mass as a variable. According to this formula, in order to work out the amount of a substance in moles, we must divide the mass of the sample of the substance by the relative formula mass of the substance. So let's consider our good friend carbon-12. We have a sample of carbon-12 with a mass of 12.0 grams. Now the relative formula mass of this substance is 12.0, which is equal to the relative isotopic mass of carbon-12, because within the sample we only have atoms of the carbon-12 isotope. However, conveniently, the relative atomic mass of carbon is also 12.0, so if you ever have a sample of carbon that only contains atoms of carbon-12, or a mixture of carbon atoms, you will always have a relative formula mass of 12.0. Okay, so let's now put those values into our formula. So we have a mass of 12.0 grams, and now we divide that by the relative formula mass, which is 12.0, and we get an answer of 1.00 moles. Let's now carry out a calculation involving carbon-12, but this time with a formula involving molar mass instead of relative formula mass. So once again, the mass of the sample of carbon-12 is 12.0 grams, and the molar mass is equal quantitatively to the relative formula mass, 12.0. However, please don't forget to include those units of grams per mole. Let's put those values into that formula now, and we have 12.0 grams divided by a molar mass of 12.0 grams per mole, and we get an answer of 1 mole. So there we go, using both of those formulas in those calculations, we have proven that indeed 1 mole of carbon-12 is present in 12 grams of carbon-12. However, we've also illustrated another point. If you ever have a sample of a substance that contains atoms of a particular element, and the mass of that substance is equal to the relative atomic mass of atoms of that particular element, when you calculate the number of moles present, you will always have 1 mole. Now the reason why this is the case is because we are essentially dividing two numbers of equal value, which, with exception to 2 zeros, will always lead to the answer of 1. Okay, let's try another calculation, this time involving the compound potassium nitrate. Now the reason why I included potassium nitrate as an example in this calculation is because it's an ionic compound. And I wanted to show that, despite the fact that the compound consists of ions, we still have to consider the relative atomic masses of atoms of the particular elements present in the compound when calculating relative formula mass and molar mass. Okay, let's carry out this calculation now using the formula involving the variable relative formula mass. So first of all, we have to consider the mass of the substance, which in this case is 5.00 grams. And now we have to calculate the relative formula mass of potassium nitrate. Now this will involve adding up the relative atomic masses of one potassium atom, which is 39.1, one nitrogen atom, which has a relative atomic mass of 14.0, and 3 oxygen atoms, which individually have a relative atomic mass of 16.0. So 3 oxygen atoms, you have 48.0. You add 48.0 to 14.0 and to 39.1, and you get a total relative formula mass of 101.1. Okay, let's now put those values into that formula. So we have 5.00 grams divided by a relative formula mass of 101.1, and we get an answer to 3 significant figures, because don't forget we round to a certain number of figures in chemistry. We get an answer of 0.0495 moles to 3 significant figures. Okay, let's now carry out the calculation again, but this time using the formula involving the molar mass rather than relative formula mass. Okay, we have a sample that has a mass of 5.00 grams, and the molar mass is the same numerically as relative formula mass, which is 101.1. But don't forget to include the units of grams per mole. Okay, so let's put those values into that formula now. So we have a mass of 5.00 grams divided by a molar mass of 101.1 grams per mole. And once again, we get an answer to 3 significant figures of 0.0495 moles. Okay, so now we know how to calculate the amount of a substance in moles. But what if we wanted to calculate the mass of a sample of a substance? And we have a sample of a substance that we know the amount of in moles, and we also know how to calculate the relative formula mass or the molar mass of that substance. However, we want to know its mass. What can we do? Well, we have to do a bit of rearranging. We have to rearrange formulas we have used previously, except this time, instead of the amount of a substance in moles being the subject of the formula, i.e. the thing we're going to work out, the mass of the sample is going to be the subject of the formula. If we rearranged our formulas to make mass the subject, they would look like this. Both of the formulas indicate that in order to calculate the mass of a sample of substance, we must multiply the amount of that substance in moles either by the relative formula mass or the molar mass of that substance. Let's try a calculation. A sample of carbon dioxide molecules consists of 1.50 moles of carbon dioxide molecules. Now we know how to work out the relative formula mass of carbon dioxide. All we have to do is add up the relative atomic mass of carbon to the relative atomic mass of 2 oxygen atoms, which in this case would involve adding 12.0 to 2 times 16.0, so you get an answer of 44.0. Now to work out the mass of this sample of this substance, we now have to multiply the amount of that substance in moles, which is 1.50, by the relative formula mass of carbon dioxide, which is 44.0, and we get an answer of 66.0 grams. Let's now work out the mass of carbon dioxide once again, but this time using the formula that consists of molar mass as a variable. So once again, we know that within a sample of carbon dioxide we have 1.50 moles of carbon dioxide molecules, and the molar mass, as we know, is calculated in exactly the same way as relative formula mass. So we get an answer of 44.0, but this time we must include the units of grams per mole. So to work out the mass of this sample of carbon dioxide, we once again multiply 1.50 moles by the molar mass of 44.0 grams per mole, and we get an answer of 66.0 grams. So there we go, now we know what the mole is and how it can be used to record and measure the amount of a substance. And we also know how to calculate the amount of a substance and express it in moles. We also know how the mole can be used to figure out the mass of a sample of a substance. I hope you all enjoyed this video. I know it was a bit rough around the edges, but it is my first video on this channel. But if you liked it, please give it a thumbs up and don't forget to subscribe to the channel. Thank you for watching, and I'll see you in the next video.